Hello and welcome. So I kept mentioning that this adjoint and the operator are sort of intimately connected and they reveal properties of each other. Why is that true? So let's start looking at the range and the null, for instance. Okay, so we always knew that the operator is characterized very strongly by the range and the null, right? Which over if you put in the entire plane as the input, what output do you get? That's the range that characterizes the operator. Similarly, null is what subspace takes you to 0. Right? So that's also very useful property of an operator to know. Now it turns out this range and null again for the operator and the adjoint are very connected. Okay, so I'm going to explore that connection in this lecture. Okay, so here is R2. Let's do it for R2 first. Okay, so I'll do it for R2 separately and then I'll do the shift to C2. It'll be quite easy, but still I think let's do for R2 because it's much clearer. So you have an operator T represented by the matrix A, B, C, D are the columns, right? Now, what is the adjoint T star? It's represented by A transpose. We know there's no need to conjugate, right? We're in R2. So it becomes AC BD, right? So the first row becomes the first column, the second column is the second row, right? So this is A and A transpose. Let's look at column space of A. Okay, so column space of A is the same as range of T, right? So column space of A, it's nothing but the span of AB and CD. Okay. Of course, you can do elimination, find a basis, etc. We know how to do that, but right now let's keep it as span of AB, CD. Okay. Now, if you look at the column space of A transpose, you get something similar. I mean, you know how to do this. Column space of A transpose is the span of AC, BD, right? AC and BD. Is there a connection to this space, span of AC, BD, and the matrix A? Okay, so from A transpose, if you want to connect this to the matrix A, what do the columns of A transpose become when you go to A? They become rows, right? So this span, this column space of A transpose is nothing but the row space of A. You see that? Right? The span of AC BD is actually the row space of A. Okay? So very simple connection between A and A transpose in terms of the range or column spaces is the column space of A transpose is the row space of A, and vice versa, right? The column space of A is the row space of, column space of A transpose is the row space of A. Okay, what will be the row space of A transpose? It will be the column space of A. I haven't written it out here, but you know it's the same thing, right? You can do that quite in a straightforward way. The column space of A will be the row space of A transpose. Okay, so very easy to see. Okay. What about null space of A? It seems a little confusing. What is null space of A? How do you relate it to A transpose, right? It doesn't seem very obvious. Here is a little connection. Now, this connection is very crucial. Once you see this connection, you will see how the intimate connection between A and A transpose or T and T star happens. So, null space of A is what? Set of all xy such that ABCD times xy equals 0, 0, right? So, this we see. Now, I am going to rewrite this. When you rewrite this, what happens? This is the same as AX plus CY equals 0. What is AX plus CY? That's actually an inner product, isn't it? AX plus CY is an inner product. It's inner product of what and what? It's the inner product of XY with AC. Do you see that? XY dot AC equal to 0 is the first equation here. Similarly, XY dot BD is 0 is the second equation here. So, the null space equation that we've been looking at all the time as a matrix equation, AU equals 0 or ABCD times XY equals 0, 0 is actually two inner products being 0. Okay, XY dot AC is 0 and XY dot BD is 0. Okay, so once you see it like this connection between A transpose and its spaces and null space of A will also be apparent. Okay, so here is the connection. Let's look at column space of A transpose perp. Okay, remember the orthogonal complement, right? What is orthogonal complement? Orthogonal complement of a subspace is the set of all vectors that are perpendicular to all vectors in the subspace, right? S perp. If you look at S is a subspace. What is S perp? The set of all vectors in R2 or C2 which are perpendicular to all vectors in S. Okay. So now how do you define column space of A transpose perp? It is a set of all xy such that this xy has to be orthogonal to everything in A transpose, which means xy has to be orthogonal to a spanning set. Is that clear? Okay, so I'm making a lot of statements here. Think about it. I want xy to be orthogonal to everything in column space of A transpose. Okay. Instead of saying everything in A transpose, it's enough if I make xy orthogonal to the basis set, right, or the spanning set. So let's say xy is orthogonal to AC and xy is orthogonal to BD, that's enough. Then clearly xy will be orthogonal to everything in column space A transpose. Do you see that? Okay. So this is how you define the orthogonal complement. So now we studied the orthogonal complement earlier. In R2 it's very small, but in general this is the idea. Okay. So how do you think of the orthogonal complement of a subspace? You take a spanning set or a basis, and then you take the xy such that xy is orthogonal to everything in the spanning set. And that gives you the column space of A transpose perp. Do you see the connection here? This equations and this equations are exactly the same. So null space of A is the same as column space of A transpose perp. The orthogonal complement of the column space of A transpose is the null space of A. It's a slightly complicated connection to think of right now, okay, but you can see the connection. It's very, very intimate, right? So column space of A is the row space of, column space of A transpose is the column space of A, and if you take the orthogonal complement of that, you get the null space of A. Okay, so that's a very nice way to think about it. You can also rewrite this in a little bit. Instead of saying the perpendicular here and its null space, I can say the column space of A transpose is actually the null space of A complement, dual of the null space of A. The orthogonal complement, the perpendicular vector that you get, the space that you get from the null space is actually the column space of A transpose or the row space of A, right? So notice all these things can turn you around a little bit, but just think about this, take your time and let it sink in. You'll see the really, really close connections between T and T star, okay? So you can push the same thing to C, okay, the complex space, except that you have these conjugations floating around. So you have to think about this slightly differently. Column space of A Hermitian is actually the span of A bar C bar. So it's actually the row space of A bar, right? So A bar is basically element wise conjugate. So you have to take the row space of A bar. So the sort of, they are equivalent in some sense. So it's not the, it's not exactly the same. You have that complement, but this complement doesn't change things too much. Okay, so it works out very, very similarly. Okay, so null space of A, you have the same thing floating around. You get the same thing, except that when you put the dot product, you will take the conjugation here, because there is conjugation in the second argument in the dot product, right? So here you don't get it. So you have to put a conjugation here. So now, but when you do column space of A Hermitian perp, that conjugation anyway comes, right? So the conjugation is here. So I want xy to be dot product with A bar C bar to be 0 and dot product with B bar D bar to be 0. So you have that already. So these two end up being the same. So here also you get this equality. Column space of A Hermitian is the null space of A perp. Okay, so that ends up being the same thing for the C2 also. Okay, so all these spaces are very, very closely connected. I'll show you one more, few more little facts that are going to come in. Here is an interesting little fact. Row space and column space of a matrix are very closely connected. Okay, so you'll see that here. Let's say we operator T represented by this A matrix here. It turns out the dimension of the row space of A has to be equal to the dimension of the column space of A. Okay, so row and column, it feels like they are two independent things. They're not really all that independent. They're quite connected. So if the dimension of row space is something, the dimension of column space will also be the exact same thing. Why is that? We'll prove it using all these things, but it turns out it's much more fundamental than that. You don't even need an inner product. Even without an inner product, this is true. Okay, so there is a slightly more theoretical proof there, but we won't go in that direction. We will use our inner product and all that and prove this result. Okay, dimension of row space of A is the same as the dimension of row space of A bar, right? So this, if you conjugate, the dimension is not going to change. And row space of A bar is sort of related to column space of A Hermitian, which is the same as null space of A perp. And then dimension of null space of A perp is 2 minus dimension of null space of A, right? So orthogonal complements and the original one add up to 2. And then what is dimension of null space of A? Use the rank nullity. You get 2 minus dimension of column space of A. This 2 and 2 will cancel, and you get dimension of row space of A to be equal to dimension of column space of A. Okay, so we're using the orthogonality and all that here. That's inner product and all that. But like I said, this result is true even without all this. You can prove it in a different way also. Okay, so maybe we'll see that later on. Okay, so this is row space and column space. The important thing to remember is dimension of row space is the same as dimension of column space for any matrix. Okay. Okay, one more property of subspace and its dual. This is an important thing to remember, that subspace and its dual can intersect only at the origin. Okay, so why is that? This proof is very easy. Supposing you have a vector which is at the intersection of S and S perp, as in V belongs to S and V belongs to S perp also. Then V dot V will be 0, right? V is in S, V is also in S perp, so V dot V better be 0. So if V dot V is 0, V is 0, right? So if you have any vector in both S and S perp, it has to be 0. Yeah, that's the important fact here. So now what do we know about column space of A Hermitian and null space of A? They are duals of each other, so they cannot intersect anywhere other than the origin. Okay, same thing with the other way around, null space of A Hermitian and column space of A, these also cannot intersect anywhere other than the origin. So because of this orthogonal complement and all that, this A and A Hermitian and all of these subspaces end up being really connected. Maybe we'll see a little bit of an example later. You'll see what I mean more clearly. Okay, so here are the 4 fundamental subspaces or associated with any matrix. The moment you have a matrix, you will associate 4 fundamental subspaces to it, and that's T and T star, of course, A and A transpose. This is how we define the thing. The first 2 are column space and null space. Okay, so column space of A is easy, right? Set of all AU for U in R2. Okay, the entire plane when hit with A goes to the column space. That's the range. Null space, all the U in R2 which give you a 0 when you hit with U, the origin when you hit with U. So that's null space. We know this. There's also row space of A. Okay, that is the third fundamental subspace. Okay, the first one is column space, second one is null space, third is the row space of A. But row space of A is also the same as column space of A transpose. Okay, when I say same, just watch out for one transposition that needs to occur, right? What is row space of A? It is U transpose A. Okay, it's actually row vectors, right? But if you say column space of A transpose is A transpose U, it's actually column vectors. So this U transpose A and A transpose U are actually the same vectors, but one is a row vector, the other is being a column vector, right? So there is a little bit of a shift there. So in fact, you can write it like this. You can say U transpose A is the same as A transpose U, the whole transpose. Okay. So there is this fact here about how transpose behaves with respect to multiplication and all that. We'll do that separately a little bit later, but hopefully you can see this very clearly here, right? So you write this out. You write for anything, what is U transpose A transpose U, you'll see that these two are transposes. One is a row vector, the other is a column vector, but the exact same things. Okay, so these are transposes of each other. So in this case, these two are equivalent. We'll just think of these two as being equal from now on. Okay, so likewise, there is something called the null space of A transpose, right? What is null space of A transpose? Set of all U such that A transpose U is 0. Now, what is A transpose U? It is the transpose of U transpose A, right? So which is the same as U in R2 such that U transpose A is equal to 0. Okay. Now this guy is called the left null space of A. Okay. So let's look at this once again closely. You have row space of A. So you have first of all column space of A. That's the first subspace. Null space of A, second subspace. Both of this we know very well. Then we have the row space of A, which is all the linear combinations of the rows. Right? That can be written as U transpose A. Do you see that? Do you see how that U transpose A works? Maybe I should just show you that, because you're seeing this for the first time here. So U is U1, U2, right? What is U transpose? The column becomes the row, you know, so U1, U2. So you have A being A, B, C, D. So what is U transpose A? It's actually U1, U2 multiplying A on the left. Okay. So normally we see AU, right? What is AU? This is A, B, C, D multiplying U1, U2 on the right. When you multiply on the right, you're going to get AU1 plus CU2, BU1 plus DU2. Okay. Now multiply on the left, what do you get? This will multiply this. You will get AU1 plus BU2 and then CU1 plus DU2. Okay, you will get a row vector like this. Do you see this? Do you see what you get when you do U transpose A and then AU? You get these two guys. Okay. So now you can also see the other things around. So you can also see A transpose U. What is A transpose U? It is ACBD, right? A transpose multiplying U1, U2. Okay. So that will give you AU1 plus BU2, CU1 plus DU2. So notice these two are transposes of each other. Right? Do you see that? Okay. And these two are different from this. You can also look at A U transpose, and that will give you something else. Okay, so when U transpose A, you can see you can't do A U transpose. That doesn't make any sense, right? So A and U transpose you can't multiply. Okay, so only U transpose A you can multiply. So A transpose U, U transpose A. I hope you saw that. Okay, so this is the other thing. Okay, you can of course do U transpose A transpose. That's a different ball game. We'll look at that later. Okay, so these are all the various quantities that are involved here. So you can see you have the row space of A, which is U transpose A for all U. Now we know that it is connected to the column space of A transpose, right? Column space of A transpose is all the linear combinations of columns of here, and that is A transpose U for U and R2. Now these two are conjugate, transposes of each other. Okay, not conjugate. These two are equivalent. Now you can also think of a null space for A transpose, right? And that will be set of all U such that A transpose U is 0. Now this A transpose U being 0 is the same as U transpose A being 0, right? Because these two are transposes of each other, right? If A transpose U is 0, so U transpose A is also 0. These two are transposes of each other, so these two have to be 0. Now this is what is U transpose A being 0? Now U transpose A is A getting multiplied on the left. What do you have to multiply on the left to get U transpose A is 0? It's a null-like space, right? So it's called the left null space of A. Okay, so you have the column space and the null space, which are sort of from the right, right? So you do AU and AU equals 0. You also have the row space and left null space, which are from the left. So you have U transpose A, all possible U, that is the row space, and then you have U transpose A equals 0, and that is the left null space. So you multiply on the right, multiply on the left, all possibilities, and equate to 0, etc. You get the 4 fundamental subspaces of R2, column space, null space, these two are from the right, row space, left null space, these two are from the left. And all of these guys are closely connected to the corresponding quantities for A transpose. Okay, so in some sort of a transpose way, right? We've seen how that works, and that is given by these guys. So row space of A is the null space of A perp. Okay, so row space and null space don't have anything other than the origin in common. So row space and null space of A are orthogonal complements of each other. Remember, row space is U transpose A, multiplying on the left all possible rows. Null space is the right null space. Okay, what you have to hit on the right to make it 0. These two cannot have any non-trivial intersection. Same thing with the column space, right? All possible combinations of columns, and the left null space. These two are orthogonal complements of each other, and they cannot have anything non-zero other than the origin in common. Okay, a lot of things to process. I know a lot of different subspaces, but very crucial, and you'll get a good handle on what the operator is from this. Okay, here are examples. I'll urge you to do each of these examples. Maybe I'll do 1 or 2 very quickly, and then we'll see how that works out. Okay, 1, 2, 2, 3. Let's begin with that example. That's very easy example, very easy example. 1, 2, 2, 3. Okay, clearly the rows and columns are linearly independent. So column space equals R2. So row space will also be R2. So once you find, so again, rows are also linearly independent, right? R2. Once you find columns and row space, the null spaces become duals of each other, complements of each other, right? So what is the null space? Null space is going to be origin and left null space. These two are duals, right? These two are perps of each other. Likewise, these two are perps of each other. The left null space equals the origin. So when you have full rank, full linearly dependent columns, the whole thing is very easy. The next example I've taken are actually not like that. So 1, 2, 2, 4. Let's do 1, 2, 2, 4 first. Okay. So you have the column space, which is okay, line through the origin, right? So what's the column space? It's a span of 1, 2. So basically y equals 2x, isn't it? Y equals 2x is the column space. Hope you see that. Okay, all linear combinations of 1, 2, 2, 4. It's span of 1, 2 actually, right? So you have to do the elimination if you remember 1, 2, 2, 4, and you'll see y equals 2x. The line y equals 2x is the column space. Okay. So what about row space? Right? Do you see what the row space is? Okay. So the x coordinate is again you're getting something very interesting, right? So you get y equals 2x again for the row space, right? So 1, 2, y equals 2x is the row space. Okay. So, what is your null space? Okay. Null space is x plus 2y equals 0. Okay. So, x plus 2y equals 0, y minus 2x equals 0. These two will be perpendicular to each other. Left null space is also going to be the same thing, x plus 2y equals 0, right. So, you put xy here, then you multiply, you get x plus 2y equals 0. So, you get the same thing. So, I hope you see this. This is for the null space. You have to either multiply it like this, xy, so which is just x plus 2y, 2 times x plus 2y, and this has to be equal to 0, 0. So, you get this. The same thing you do on the other side. You do xy 1, 2, 2, 4. So, you see there is this symmetry here, right. So, you get this. So, this would be x plus 2y, 2 times x plus 2y, and that is 0, 0. So, you get x plus 2y is 0. So, you see here all of these things became sort of the same, one and the same, the left null space, right null space. So, such interesting things will happen. Let us see the last one, minus 4 minus 8 2 4. So, this one. Okay. So, what about the column space and row space? Column space is x equals minus 2y. Do you see that? X plus 2y is equal to 0. Row space is also x equals minus 2y. Is that correct? No. X equals minus 2y is the, oh yeah, you're right. I think x equals minus 2y is the row space. Oh, no. Row space is something else, right? So, column space is minus 4 minus 2. Row space is minus 4 minus 8. So, it becomes y equals 2x. Okay. I hope you see this. Okay. Hope you see that. So, column space was a span of minus 4 comma 2. So, that is x is 2 times y, minus 2 times y. Okay. Now, row space is span of let us say 2 4, and that is y equals 2x. Okay. So, I hope you see that. Null space we have seen before is the same as, right, x equals minus 2y. Okay. And the left null space, you can guess, will be y equals 2x. Okay. So, check these things out. These are interesting things to think about. You can just solve for the null space like we always do, and you will get these things. So, notice how these two are perpendicular complements of each other. These two are perpendicular complements of each other. You can plot them and see. You will plot a line. You will get y equals 2x is something here. Y equals minus x by 2 is something here, and this angle will be 90 degrees. Okay, so this is y equals 2x and y equals minus x by 2. Okay, so these two are perpendicular, those two are perpendicular, and one of them is the column space and row space as well. Okay, so I hope this gave you a good idea about the 4 fundamental subspaces of a matrix and how that relates to the adjoint also. Right, the adjoint also will have 4 of its spaces, and all of these are very, very closely connected. Okay, thank you very much.